Hello, welcome to Vedil Vagupare. In this video, let us see an interpretation of a question which is taken from GATE 2025 question paper. So we will interpret the NMR and IR data given in this particular question, and we will also learn the basic informations pertaining to these data. So let's see the question first. A compound K displayed a strong band at 1680 centimeter inwards in its IR spectrum. Its proton NMR spectral data are as follows. The correct structure of the compound is. So in this particular question, an IR data is given and then a set of chemical shift values of the compound is given, and they are asking us to interpret the compound. So here we have four different compounds given to us, and we have to match these data with these compounds and then find out which of these options are the correct options for this particular question. So before we go into solving this particular question, let us see some background information about certain parameters pertaining to IR and NMR spectroscopy. So while interpreting an organic molecule in an using an IR spectrum, you know that there are characteristic bands which describes about certain functional groups. And we see in these four molecules, the carbonyl functional group is there, ester functional group is there, ether functional group is there. So we will see some, some data pertaining to where these kind of functional groups will be seen in an IR spectrum. And then we'll also see about what does the value J mean and what can we interpret from these data that are given here. And also we obviously know that the chemical shift value is a characteristic value of a proton of a particular type. So we will also look into all these basic informations, and then we will solve the four options here to find out which of them is the correct answer. So let us take these data. Let us take the IR absorbance. So the question says compound K displayed a strong absorbance or strong band at 1680 centimeter inverse in its IR spectrum. So we know pretty well, because all of the compounds that we saw had a carbonyl group, and the carbonyl group were either an aldehyde, ketone or ester. So first we have to rule out the possibility of whether the compound is an aldehyde, ketone or an ester. So for that, let us see the characteristic values at which, absorbance values at which we will see the peaks for the aldehyde. So the aldehydes are usually seen at 1730, and based on the conjugated groups that are present along with the carbonyl group, the values decrease. It is the same for all the other categories. Whenever there is a conjugated alpha beta unsaturated ketone or an aldehyde, you will see the absorbance value decrease. Similarly, an aromatic aldehyde or an aromatic ketone or an ester will also have a conjugated pi electron system, and as a result, it also shows a lower absorbance values. So the lower value is because of delocalization of the pi electrons, which leads to weaker bonds, and as a result, you see the values at a lower value. And now coming to the now coming to the absorbance values, we see that in the question it is given as 1680 or 1680. So in this particular set of values that we have noted down, we see aldehydes and esters are always absorbed at around 1730 to 1705, both for aldehydes and esters. But in case of ketones, it starts from 1715 to goes as low as 1690 or 1680. So here in this particular case, we see that the value is 1680, and probably the given compound has a alpha beta unsaturated ketone structure or an aromatic ketone structure. So we will go to the next slide to find out how this can be matched up with the given structures. So now when we look at the molecules, all the four molecules, aldehyde is ruled out, and of course ester is also ruled out. And because we know that both aldehyde and ester gives value around 1700, whereas the value given here is 1680. And we have seen that aromatic ketones absorb at around 1690, and here our value is 1680. So the most possible compounds are C and D, which has a keto group in their structure. So among the four, two of the molecules are ruled out because the IR value does not match an aldehyde, nor does it match an ester. So the possible molecule should be C and D. So now using NMR data, we will try to find out which among the two is the correct answer. So before going into the solution, let us see some basic information about the coupling constant or the J value, which is given here. And we know that J is nothing but a spin splitting factor. And this spin splitting factor or splitting is a phenomenon wherein there is a magnetic interaction between the neighboring non-equivalent protons. And we make use of the n plus 1 rule to find out the num number of ways in which a particular signal could be split. And the distance between the split signals is called as the splitting constant J value, and it is expressed in hertz. And let us take an example here. Let us try to understand this with an example that is given here. In this particular molecule, this is actually um, a, a dichloro substituted compound in the second carbon, and in the first carbon you have a single chlorine atom. So in other words, we see here there are two types of protons, and both the protons are two types because they are non-equivalent. Two neighboring protons are non-equivalent, and these neighboring protons, when they are non-equivalent, they will split the signal of the proton. So here we see the Hb signal is split by the two non-equivalent protons in the neighboring carbon atom, and so it is split in, as per the n plus 1 rule, it is split into 3. So it is 2 plus 1, which is equal to 3. So it is a triplet. And likewise here the Ha protons have a neighbor 1, so it is 1 plus 1, which is equal to 2, and so this is a doublet. And we know this intensity of the peak is in the ratio 1 is to 2 is to 1, whereas here it is 1 is to 1, based on the uh, uh, Pascal's triangle that we have studied, and we know how it is done. We will see in another video on all of these. So having understood this, because these two protons are coupled protons, the distance between these two peaks and these two peaks are same. See, it is 6.1 and it is also 6.1. Similarly, the distance between the two doublets is also 6.1. So whenever you have the same value for a particular signal, two sets of signals, then it means the two protons or the two signals are due to the coupled protons. So the J value is an excellent way by which we can easily identify whether the given chemical shift values are for a coupled proton or not. Besides that, the J value also helps us to find out whether the molecule is a cis isomer, trans isomer, and many other types of protons could be very easily identified making use of the J value. And here, because it is between two neighboring protons and it involves three bonds, like say for example Ha to Hb, there are three bonds involved. That is why the superscript 3 is used. So all normal non-equivalent interactions are all 3 JAB type of interactions, and in this particular case the J value is given as 6.1 Hertz. And it is, and we must also note chemical shift value is expressed in parts per million, whereas the J value is always expressed in Hertz. So now let's see the J value, characteristic J value for certain types of protons. So this is a typical acyclic proton. So when two non-equivalent protons in an open chain are coupled, the J value is around between 6 and 8. But when it is a vinylic trans, we see the J value is 18, 11 to 18. And if it is cis, it is between 6 and 15. And if it is on a germanyl carbon, then it is around 0 to 5 hertz. So here in this particular case, because it is on the same carbon, see here the superscript J says very clearly the two protons are non-equivalent protons on the same carbon atom. Whereas all of these are neighboring carbon atoms. But in a germanyl carbon, the protons on the germanyl carbon, when they are non-equivalent, their J value is between 0 and 5. Similarly, when we see the aromatic protons can be either called as orthoprotons or metaprotons. Of course, paraprotons are there, but then their interaction will be very, very minimal or zero. So when there are two protons next to each other, they have an interaction. Obviously, we know they are non-equivalent. If they are non-equivalent, then their J value is between 6 and 10. Whereas when they are on alternative carbon, or they are called as metaprotons, the J value here, this is also called as long range coupling because the J value exceeds 3. So here you see 1, 2, 3, 4. So such kind of interactions, when it is possible, the J value will help us to understand that there is an interaction. And of course, there will be a splitting of the signal of each other's signals possible. And this is another aldehyde proton wherein the J value is between 2 and 3. So having understood the details of standard J values, we will now see the problem. So in the question, we have molecules and they have given us a set of NMR chemical shift values. So we will just sort them out into a particular format and then we will discuss the question. So in this particular question, we see there is a J value. So we will sort these data based on the J value. As I told you, by looking at the J value, we can find out the coupled protons. So in this particular question, you see the J value 7.2 is given here. And there's another chemical shift which also has a J value 7.2. So it means these two protons are coupled proton. So I am including these two into one data. Similarly, we see the next J value which is 7. And there's another data, a chemical shift value which also shows 7. So we will club them together and then we will keep them together so that we can understand these two signals. And then finally, there's one signal which doesn't show any J value. It means it is an uncoupled proton. And obviously, we see from the data that is given here, these are doublets, and we see 3.8 is a septet, and then at 1.9 it is a doublet. So obviously, these are all coupled protons, and this is a singlet. It means there is no coupling constant or J value to this. So now that we have grouped these data, NMR data into sets of coupled protons, now we will try to match the structure of the molecule with the NMR data. Usually, when you are solving these combined problems, it is very easy for us to use IR spectral data to just shortlist or rule out which will not adhere to this particular data. And then using NMR, we can come to the conclusion of which among the two which we have shortlisted could be the answer. So here in this particular case, as we have said, it is ortho protons. These are because there are only two, all of them are para substituted, and of course because they are para substituted, we know the aromatic protons are actually orthoprotons. So in C and D, A and B also has only orthoprotons. So I am not looking at A and B because of IR data has ruled out these two molecules. Otherwise also, when you look at A and B, you will see that they also have orthoprotons. So obviously the two orthoprotons have a neighboring proton, and these neighboring proton couples it, and that is the reason why it is a doublet. So there is a signal due to orthoprotons, two sets that we have here. And of course, one value is set to 7.3, another is 6.8. which we will have to make out whether is it because of, as you know, in this particular case, there is oxygen on one side, this is oxygen on one side, and this is a carbonyl group on other side. Likewise, on this molecule also there is a carbonyl group and there is an oxygen. So in both the category, we see carbonyl and oxygen are on both sides. So uh, here we are unable to fix up which of these is being talked about. But then we know that the two sets of protons are due to the aromatic protons, and as a result, we know this set means that there are two sets of orthoprotons. Now coming to the next. So in this next set of data, we see this one proton is a septet and these six protons is a doublet. Obviously, when we look at these molecules, this particular area where we are having this isopropyl group, this place, we have two methyl groups, and the two methyl groups is contributing to the six protons, and there is a CH group here, and so it contributes to one proton. So in both the categories we have this data which is due to the methyl groups of isopropyl group and the CH group, and it is the same in A and B also. And of course we know they are coupled because CH is coupled with the six protons, so that is why it is septet, whereas the methyl proton is coupled with the single proton, and so it is a doublet. So we know that it is the same in all of these molecules, and that is how we have this particular structure. So next, coming to the last category wherein it is a singlet. So this singlet, we have to see that this particular methyl group and this methoxy group, they are not having neighboring protons, and so definitely both of them are having CH3 groups, so it is due to three protons and they will be singlet. Now the question is about the position or the chemical shift value. So it is very interesting to see in both C and D, we have the carbonyl group and the ether group. But the question is, which carbon are we talking about? And based on this chemical shift values, we can very easily make out whether the given molecule is C or D. So let us see another example. So it is seen from chemical data that if a proton is next to a carbonyl group, its value is seen around 2. When the proton is next to an electronegative oxygen group, carbon more than carbon, oxygen is more electronegative. And so it is seen at a even higher chemical shift value, which is around 3.65. So if a carbon is next to a carbonyl group, the value is around 2. If it is next to oxygen, the value is around 3.6. So here we are seeing this particular carbonyl group, uh, aceto group, is actually around, should show chemical shift value around 2.1 to 2.6. Similarly, this is an ether group and it must show values around 3.3 to 3.9. Likewise, it is opposite in this particular molecule. So this will be 3.9 and this will be 3.2. So now, with having understood these things, let us go back and look at these two substituents and their chemical shift values. And we see here in this particular molecule at 3.8 septets, at this place 3.8 septet, which is due to one single proton. Okay, we can match only this structure because only here this group is next to the electronegative oxygen. So this methylene group, this methine group will be seen at or between 3.3 and 3.1, whereas here this methine group is actually next to a carbonyl. So this methine group will not be seen at 3.3, it will be seen at around 2.1 to 2.2. And of course, these this is not possible. Similarly, let us go see the carbonyl group of at the bottom. So here we see the methyl group must be at around 2.1, and because it is not having a neighboring proton, the value will be a singlet. The split, there is no splitting, and it will be a singlet, and it is due to 3 protons. Similarly, here it is also a singlet and due to 3 protons, but it will not be observed at 2.1, rather it will be observed only at 3.3. So as a result, this singlet does not match with the chemical shift value presented here. And so the answer for this particular question will be C. So let us look at have a summary or a quick summary of this particular question. So this question has given an IR data and then a set of NMR data. And what we saw was from the IR data, the IR data shows very clearly that the compound is a keto group and not a ester or an aldehyde group. So the option is either C or D. So between C and D, we see that the J values were matching that of the aromatic protons. So the aromatic protons does not give us any clue as of now. Similarly, the other sets of protons also do not give us much of a clue because again they are coupled protons, and these coupled protons are due to 6 proton and 1 proton. So here we see this isopropyl group is present in both the cases, and so they will also be giving a septet and a septet and a doublet as predicted. So altogether, the J value does not help us with the information, nor the splitting pattern does not help us to solve the question, but the position of the chemical shift value or position of the signal, the chemical shift values greatly helps us to solve this particular problem. So in this particular molecule, we see that at 2.2, we get a singlet. So the singlet will be seen either for the methoxy group or the acetate group. So the question is, where will the acetate group appear in an NMR spectrum? Where will a methoxy group? It is seen it is only the acetate group that appears at around 2.2. Whereas the methoxy group, because it is next to an electronegative oxygen, will appear beyond 3.3 to 6, 3.6. And as a result, from the given data, we can very easily conclude. We don't have to solve the others at all. We can very easily conclude C is the correct option in this particular question. Besides that, when we look at this isopropyl group also, we see here again the oxygen which is bonded to the methane group. So because the oxygen is bonded to methane group, we know the value is around 3.8. As I told you, if it is of ether group, it will be at a higher value because of the electronegativity of oxygen. So the exact value match of the chemical shift value with that of the particular functional group proves that option C is the correct answer. Hope you understood. Thank you. Please subscribe for more videos.